Welcome to another edition of Math Help with Mr. Pi. Today we're going to be talking about theoretical probability. If you happen to be working out of the Prentice Hall textbook, copyright 2009, this is lesson 2.6. So let's get to it. The probability of an event, or P of the event, tells you how likely it is that an event will occur. An outcome is the result of a single trial, like a roll of a die. The sample space is all possible outcomes. An event is any outcome or group of outcomes. Now, if we take a look at this die, if you roll any single die, you're going to get a number 1 through 6. That's going to make the sample space be 1, 2, 3, 4, 5, or 6. This is our sample space. All possible outcomes, that's a total of 6. If I said, let's find the probability of rolling a 2, the favorable outcome would be a 2, and the actual probability then will be equal to 1 over 6. Now, how do we get 1 over 6, you may ask? That comes from the definition of theoretical probability. Here's a definition of theoretical probability. The probability of an event is equal to the number of favorable outcomes divided by or over the number of possible outcomes. In the example we just looked at, I said, what's the probability of rolling a 2? The favorable outcome is a 2. We can see a 2 right here. So that would be 1. And the total number of outcomes would be 6 because our sample space is 6. 1, 2, 3, 4, 5, or 6. So the probability of rolling a 2 is 1 to 6, or 1 over 6, 1/6. Because probabilities are defined as a fraction or a ratio, they can be written as decimals and percents. All probabilities will have a range from 0 to 1. The closer to 1 the probability is, the more likely the event is going to happen. The closer to 0 the probability is, the less likely the event is going to happen. So all the time, probabilities are going to be some kind of fraction, some kind of rational number between 0 and 1. Here's example 1t, finding theoretical probability. Now, the T stands for teacher, meaning me, Mr. Pi. I'll do this one. There will be one for you to do. I'll explain that in a moment. A bowl contains 12 slips of paper, each with a different name of a month on it. Find the theoretical probability that a slip selected at random from the bowl has the name of a month that ends in BER. Well, we got to know that there are 12 months, so we need to first write this out in a probability notation. The probability that the month ends in BER and that's going to be equal to something over 12. Now I say something over 12 because we got to figure out how many months end in BER. We know there are 12 months in the calendar year, therefore our sample space is 12. Now the months that end in BER, September, October, November, December. That makes a grand total of 4. Now the probability is 4 over 12, or 4 out of the 12 months end in BER. But probabilities, because they are fractions, should be reduced or simplified, meaning that finding a common factor of 4 and 12, which would be 4, that means I need to divide both the numerator and the denominator by 4 to get the reduced probability. 4 divided by 4 is 1, and 12 divided by 4 is 3. So the probability that a slip of paper is going to have a month that ends in BER is going to be 1/3. Here's example 1S, finding theoretical probabilities. You select a 3-digit number at random from the set of all positive 3-digit integers. Find the probability of each circumstance. Before we even find any probabilities, we have to define our sample space. So I'll do that work up here. The problem a lot of students have with this particular problem is figuring out the sample space. We select a 3-digit number at random from the set of all positive 3-digit numbers. Well, positive 3-digit integers. The first 3-digit integer is 100. The last 3-digit integer is 999. To figure out this sample space, I'm going to give us an easy example to start with, and I'll do that over here in green. How many numbers are there from 1 to 10? And of course, you're going to say, well, there are 10 numbers from 1 to 10. If we find the difference between 1 and 10 by subtracting 10 minus 1, well, that's equal to 9. That's not how many numbers are in between them, even though we say in between and we think difference. That's not exactly accurate. What we need to do to find how many numbers there are between two particular numbers is first we subtract them, then we have to add 1. So the number of numbers from 1 to 10 is 10, and we can find that by going 10 take away 1 is equal to 9 to get 10. Now, relating that to this example here, if we take 999 and we subtract away 100, that gives us 899 numbers. Well, that's not exactly accurate. We need to take that and add 1 to it, which gives us 900. Our sample space is 900. And we found that by taking the larger number, subtracting away the smaller number, and that gave us the difference. Then we add 1 to get our actual sample space. So our denominator in each one of the following examples is going to be 900. Now, the first one here is the probability of a multiple of 20. We know our denominator is going to be 900. Now we have to figure out the favorable outcomes. This is the total number of outcomes. We have to figure out the favorable number of outcomes. And to do that, I'll make a little list. The multiples of 20, starting at 100. 100 is a multiple of 20. 120 is a multiple of 20. 140 is a multiple of 20. 160 is a multiple of 20. And 180 is a multiple of 20. We can repeat that process for 200. We'd have 200, we'd have 220, 240, 260, 280. We could do that for 300, for 400, for 500, but there's no need to list them all out because we know for every 100 there's going to be 5, and we have 9 hundreds. So to figure out our numerator, we're going to go 9 times 5, which is equal to 45. 9 is because we were working with 900s, 100, 200, 300, all the way up through 900. And there are 5 multiples of 20 for each 100, so our numerator is going to be 45. As we saw in the previous example, we are certainly going to need to reduce our fraction here. And 45 over 900 can reduce by a factor of 45. 45 divided by 45 and 900 divided by 45 gives us our reduced solution here, which is 1 over 20, or about 5%. So the probability that we're going to select a multiple of 20 is 1 over 20. The probability of not a multiple of 50. Keyword here is not a multiple of 50. We don't want a multiple of 50. So first it's going to be easiest, I think, to find the probability or the number of multiples of 50s and then subtract. multiples of 50 like we did with the multiples of 20, we can first have 100 and 150, 200, 250. So for each 100, there are two multiples of 50. So for each 100, there are two multiples of 50, and we have 900. So 2 times 9 is equal to 18. There are 18 multiples of 50, but we want to know the probability of not a multiple of 50. So we take 900 and we subtract away from that 18, and that gives us 882. That's our denominator. This is our favorable outcomes. There are 882 numbers that are not multiples of 50. And again, we're going to need to reduce that fraction. And that fraction does reduce to 49 over 50.